Welcome back, design junkies, to Mechanical Engineering Made Simple. Today, we're going to pull back the curtain on the world of manufacturing. We're going to reveal the hidden language, the secret grammar that lets us turn a simple idea into millions of identical, perfect parts.
Right? I mean, that is the multi-billion-dollar question. And the answer? It isn't just about bigger machines or faster robots. It's actually about a deep, really elegant system, a kind of grammar for how we make things. So let's just dive right in and uncover the systems that make our whole complex world even possible.
Okay, so before a single piece of metal is ever cut, the battle against chaos has already started. And the very first step is to bring some order to that chaos. We do that through classification. You can think of it like creating a giant library for parts, where every single component has its own specific logical address.
Now, this is where it gets really powerful. The sheer scale of the savings here is just mind-boggling. By simply organizing parts into logical families, a company can stop redesigning the wheel over and over again. And get this, 80 to 90% of features on a part are often just a specific designer's preference, not functionally necessary. So when you standardize, you create this massive opportunity for efficiency. It is the foundation for absolutely everything else that follows.
So how do we actually build this library of parts? Well, it really comes down to two fundamental ways of thinking. First, you've got the E-tree. This is like a game of 20 questions. Is the part rotational or is it not? Does it have a hole all the way through? Yes or no? It's a branching tree of simple choices. On the other hand, you have the N-tree, which is more like a checklist. It's all about description. It just lists attributes. Does it have a bevel, a flange, threads? It's basically creating a detailed profile for the part, like a character sheet in a game.
And check this out. This is how those abstract systems turn into a super powerful code. A single number can instantly tell you the general size of an object. A code of 3? That's something that fits in your hand. But a 9? Yeah, that's something you could park a pickup truck inside of. It's an incredibly dense shorthand for communicating scale.
All right, let's keep going. We've got our blueprints all organized. Now it's time to actually make something real. We're talking about the fundamental act of creation, transforming a boring block of raw material into a precise, functional shape. This is where the magic happens.
You know, at the very heart of shaping metal, there are basically two opposing philosophies. Do it hot or do it cold. Hot working is all about shaping the metal when it's glowing red and malleable. You heat it up, which makes it easier to form, and the process actually makes the final part stronger. Now, cold working, that's all about refinement. It's done at room temperature, takes way more force, but what you get in return is an amazing surface finish and super tight dimensional control.
Forging is the classic example of hot working. Just think of a blacksmith's hammer, but on a massive industrial scale. You're squeezing a hot piece of metal with such extreme pressure that it flows and perfectly fills the shape of a die. The force you need is enormous, and it all comes down to a really simple relationship. The more complex the shape, the more force you need. The stronger the material, you guessed it, the more force you need. And of course, the bigger the part, the more force you're going to need. It's a really intuitive balance.
Then you have rolling, which is an absolute workhorse process. This is how we get the vast majority of our sheet metal, plates, all that stuff. It's kind of like a giant industrial rolling pin. A heated slab of metal gets passed between these two huge rollers, and they just squeeze it down to the exact thickness needed. It's simple, it's super effective, and it happens on a truly massive scale. Now this one is cool. Think of extrusion just like squeezing toothpaste out of a tube. You take a big cylinder of metal, you push it with incredible force through a specially shaped die, and what comes out the other side is a long, continuous part with that exact complex shape. This is how we get things like aluminum window frames or intricate cooling fins, anything with a complex profile that needs to be really long. But of course, not all shaping starts with a solid chunk of metal. The other huge family of processes is casting. This is where you start with molten metal. Whether you're pouring it into a simple sand mold for a one-off part, or you're injecting it under intense pressure into a hardened steel die to make millions of them, the basic principle is exactly the same. You start with a liquid, and you end with a solid. Okay, so we've organized our parts, we've created their shapes. Now for the big one. How do we connect them together so they don't fall apart? This brings us to the unsung hero of the mechanical world, the humble bolt, and the truly fascinating physics that makes it so incredibly strong. So let me ask you a question. What actually happens when you pull on a bolted joint? I mean, it seems obvious, right? You pull, the bolt stretches, and if you pull hard enough, it breaks. But the reality is so much more clever than that. The way the bolt and the parts it's holding work together, it's a dynamic system, and it's designed for incredible strength. The magic word here is preload. See, when you tighten a bolt, you're actually stretching it. You're turning it into a very, very stiff spring. And at the exact same time, you're squeezing the parts of the joint together. Preload is that perfectly balanced state of tension in the bolt and compression in the joint. It's this built-in tug-of-war that's happening before the joint even does any work. And it is the entire secret to its strength.
Okay, so let's walk through this. Picture it. An external force comes along and tries to pull the joint apart. But here's the trick. That force doesn't immediately yank on the bolt. No. Its first job is to fight against the compression that's already in the joint. It has to undo that squeeze first, so the joint members relax and expand just a tiny bit. It's only after that initial preload compression is totally overcome that the bolt itself finally starts to feel a major increase in tension. That preload is basically a massive invisible shield protecting the bolt.
And this quote right here is the reason why it all works. The joint itself, the parts being clamped, is way stiffer than the bolt. So for any given force, the joint can handle much more of it without deforming. This means the vast majority of any external load just goes into decompressing the joint, while the bolt, the thing we're worried about fatiguing and breaking, is almost completely shielded from all those crazy fluctuating forces. It's genius. So let's zoom out and bring all these ideas together. We've gone on a journey from an abstract system of organization to the fire and force of the forge, and finally all the way down to the hidden physics of a single connection.
It really boils down to this: organize, create, connect. That's the grammar of production. First, you organize the chaos with these smart, logical classification systems. Then you create precise shapes from raw material using incredible processes. And finally, you connect those parts together using a deep understanding of the physics involved. It's like a 3-act story that literally builds the entire world around us.
And that's what I want to leave you with. Think about it. The chair you're sitting on, the phone or computer you're watching this on, every single bit of it is a product of this deep, invisible grammar. So the next time you look at any manufactured object, just ask yourself, what unseen systems of organization, creation, and connection had to be absolutely perfected to make this thing in my hands possible?